Hey, Science, and welcome to topic 3.2 of the Space Exploration Unit. We're going to be discussing using technologies to see beyond the visible today. Last day I talked to you about optical telescopes, which allow us to see very faint, distant objects in the sky that we can actually see in the visible light spectrum. But what about things that we want to see that are beyond the visible light spectrum? You got to remember that visible light is only one form of what we call electromagnetic energy. Electromagnetic energy, as the name implies, has electrical and magnetic fields tied to it. As you might remember in our electricity unit, in Unit D, I discussed the fact that electrical fields will generate magnetic fields and magnetic fields generate electrical fields. Well, that's what this form of energy does. It's essentially two fields combining together to form this form of energy. Now, visible light is a form of electromagnetic energy, but there's other forms as well. Visible light is only a very small section of what we call the electromagnetic spectrum, which you can see down here on the bottom of the diagram. Visible light makes up like just a very narrow band, and that's what we see because our eyes are designed to see visible light. But there's all sorts of other types of electromagnetic energy that we can't physically see, but we can use technologies to detect them. Well, what types of energy am I talking about? Well, you can talk about radio waves, microwaves are in there, infrared. You might have heard of infrared, ultraviolet, which we talked about with the ozone layer in Unit C, X-rays. I mentioned a little bit about X-rays last time, and also gamma rays, which you might be familiar with if you're a fan of the Marvel movies and Mr. Incredible Hulk. I don't have the Hulk on my shirt today, but one of the cohorts here of Captain America and Iron Man, Mr. Bruce Banner, got exposed with gamma radiation to form that lovely green behemoth that we like so much. If you're a fan of the Marvel movies, I would recommend you don't expose yourself to gamma radiation because it tends to be not as good for people in real life. It tends to kill you if you get exposed to high levels of gamma radiation. But anyways, all these forms of electromagnetic energy that we can't see, we have specific telescopes that are designed to actually pick up these forms of electromagnetic energy. Now, all of these forms of electromagnetic energy are all flying through space at essentially the speed of light, which is 300,000 kilometers per second. So when we talk about light speed, technically, light is basically every form of electromagnetic energy. We're not just talking about visible light here. It's also radio waves in space, microwaves in space, infrared, UV, all of them. All of these forms of electromagnetic energy that are emanating from like stars throughout the entire universe, or black holes, or whatever's producing these forms, which is generally speaking are going to be your stars, or stars that are in either that are living out their lives, or stars that are in the process of dying. It could be a super red giant, it could be a white dwarf, it could be a neutron star, but they're all going to produce various amounts of these forms of energy that we can then detect on Earth using specialized telescopes. So in this case, we can use telescopes like radio telescopes. And radio telescopes have the great advantage of you can use them 24 hours a day, 7 days a week, 365 days a year. Because it's radio waves, they don't have to use these telescopes that are on the ground at night. Right? If it's a visible light telescope, an optical telescope, you can only use them if the skies are clear, if it's dark outside. Radio telescopes can basically pick up signals from the universe, these types of electromagnetic energies, 24 hours a day, because again, radio waves are invisible, and it doesn't have to be dark in order to detect them. So that's a huge advantage of these telescopes that see beyond the visible light spectrum, is that they can be used at other times of the day when normally an optical telescope would be useless because the sun's out. You can't see objects in the night sky because it's too bright out because the sun is there. Now, radio telescopes are among the biggest telescopes in the world. There is one radio telescope here. You can see it on the diagram there. It's in China. It's actually built into the side of a hill or a mountain in China. And that telescope has a diameter of 500 meters, so half a kilometer. Compare that to the largest optical telescope that I talked to you about, which would be the very large array, or the extremely large telescope, I should say, that's being built in Chile for 2025. That has a diameter of only 39.3 meters. So this is easily 10 times bigger in diameter. Now, these telescopes have to be large because radio waves are the longest wavelengths of electromagnetic energy, so they're very long. So we require large telescopes in order to pick up these very large waves. Otherwise, you could literally, a wave could pass right over a telescope and you wouldn't even detect it if it wasn't big enough to do so. So that's what radio telescopes do. And as well, they can also be, these telescopes, these radio telescopes can be daisy chained. As I mentioned last day, we can use the technique of interferometry, which is basically taking several telescopes together to increase their resolving power. An example of this is what I did mention earlier by mistake, which is the Very Large Array, which is found in New Mexico. And that's actually a photograph of the Very Large Array right there. It's using 24 radio telescopes, and they're 25 meters each in diameter, and they're in a large Y pattern in the desert in New Mexico, and they essentially cover a distance of roughly 61 kilometers in the desert. By doing this form of interferometry, they're basically creating that one telescope with all these telescopes. It would be the equivalent of a single telescope that had a diameter or a mirror that's 27 kilometers in diameter. So that's a very impressive resolving power for this set of radio telescopes that's found out in the New Mexico desert. I also mentioned as well last day, it's not in the notes, but I do like to talk about this telescope. There's the Chandra Telescope. It's an X-ray telescope. It's in orbit around the planet up there with Hubble, and it's basically detecting a lot of, it detects X-rays, and it comes up with some amazing images that normally we can't detect. Things that a star that we see with visible naked eye looks completely different when you see the X-ray bursts that are being produced by things like black holes and neutron stars. It can allow us to detect the presence of these very small objects. We can't necessarily see them, but by the amount of X-rays that are being produced, we can deduce that there are, in fact, these objects in certain parts of the night sky. And if you're interested in Chandra, there is actually, if you're on Instagram, you can actually follow the Chandra Space Telescope on Instagram. So if you type in, I think it's NASA Chandra Telescope, or if you type in Chandra Telescope on Instagram, there is a feed for, and there are some of the pictures are amazing. It really is an amazing feed if you're an Instagrammer. So take a look at that. One other thing you can do to make objects that are invisible visible is to bring the object closer to you. Now, we can't necessarily take the planet Jupiter and bring it into Earth's orbit. That would probably not be a good idea, even if we could do it. But what can we do to bring a planet like Jupiter or Mars or the Sun or Mercury or the moons around Jupiter or the Neptune? How can we bring them closer to Earth? Well, we basically send out probes. We send out space probes to them, and we've discussed this already earlier in the course. Pretty much every planet in the solar system has been visited by some kind of an unmanned probe through the entire history of space exploration, here on Earth. And there's a lot of exciting new space probes that are going out there. Now, some of the space probes you might be familiar with, Mariner, which made a lot of big discoveries in the 1970s on Mars. Voyager is probably the most famous one, Voyager 1 and Voyager 2, that took the first two big journeys through the solar system. Voyager 2 is still the only probe to actually have reached Uranus and Neptune. It's the only time we've seen those planets up close. It also saw Saturn and Jupiter as well. So they're very famous space probe. There's actually a documentary it was on Netflix at one point. If it's not there, maybe take a look. But there's a whole documentary on the building of Voyager 2 and the missions that the Voyager spacecraft undertook. Definitely worth a watch if you're a fan of space exploration. But more recently, there's been some really exciting probes coming out to do exploration, and there's continued research on unmanned probes to Mars. There's right now the European Space Agency is looking at trying to land a probe on one of the Jupiter's moons, Europa, to actually dig into the ice to look for signs of life there. So that's a very exciting probe that's coming up here in the next decade or so. But right now, there's a couple of probes that are just getting active or just finishing their missions or continuing on their mission. So one of them right now is the Parker Solar Probe, which was launched in 2018, and it's been basically sent to enter the sun's corona. This is going to be the closest probe that has ever explored or looked at the sun, and it had some state-of-the-art technology to do this, because you can imagine getting that close to the sun, the temperatures are going to be extreme. They've got basically cooling systems and heat shields that basically keep the probe at room temperature uh, as it flies around the sun through this really hot area of the sun called the corona. And that area, by the way, has temperatures of about 1.5 million degrees Celsius. So we're able to keep this probe at room temperature, even in temperatures of 1.5 million degrees Celsius. So that's pretty impressive technology there. And if you're interested, just Google that. The Parker Solar Probe would be one to look at there. Another one that's had some really cool press over the last few years has been New Horizons. New Horizons was the first probe to rendezvous with the dwarf planet Pluto, which used to be the ninth planet. It's not the ninth planet anymore. But it rendezvoused with Pluto in 2015. And then it went out into the Kuiper Belt, which I talked to you about earlier in the unit, that extended area beyond the orbit of Neptune, all the way out to the Oort cloud, which is the edge of the solar system. And it rendezvoused with another object, which is right here, called, I'm going to get this wrong, it just got renamed actually this year. It was another name last year. Now they just renamed it this year or a couple of years back. It's called Arrokoth. Arrokoth is the name of this object. And this has been a huge find for NASA. It's a very small object in the Kuiper Belt, but it basically shows that how the formation of objects in the solar system have occurred, how two objects that are round basically have come together. And there doesn't seem to be any kind of destructive force here. It's almost like these two objects just sort of kind of gently came up beside one another and parked beside each other and became one object. There's no stress fractures where the two objects have met. So this is really kind of giving NASA scientists a great, they're showing them how, in fact, a lot of objects in the solar system may have come together very gently as they formed over the eon. So it's sort of a great way for NASA to look at the formation of the solar system, how objects and how planets formed, billions of years ago. Right now, it's also detected, it's also confirmed the existence of a hydrogen wall at the outer edge of our solar system, which is essentially the Oort cloud. That was speculated by when it was first detected in 1992 by the two Voyager probes that had been launched from Earth back in 1977. So it has been able to basically make more accurate measurements. And as it moves out further toward the edge of the Oort cloud, hopefully we're going to make more discoveries about not just the Kuiper Belt, but the actually outer edge of the solar system, which I mentioned extends like 3 light years away from Earth. So, I mean, it's not going to hit the edge of the Oort cloud or the Oort cloud by our lifetime for sure, but it's certainly going to be doing some great exploration in that Kuiper Belt for many years to come here as it heads further out to the far reaches of the solar system. So yeah, that's basically that, and that's basically our topic today about using technology to see beyond what is visible in the night sky. For homework, I'd like you to complete questions 1 to 5 and number 7 on page 445 of the Science in Action 9 textbook. That is the discussion for today. Tomorrow, our next day, whenever you decide to watch the next video, I'm going to be finishing up topic 3 with topic 3.3, using technology to interpret space. We'll be discussing how we can measure the distance of stars from the Earth. How do we actually do that? I'll tell you how we do it. It's called math. Pay attention in your math class. That's it for today, everyone. Have yourselves a good one, and we'll see you soon.